there are two videos, right? I think I
Yeah,
did
yeah.
one. I think I could not do the last one, but yeah, I've read it, so I think
Okay,
that
the
should
one on
be
metal semiconductor junctions and things.
yeah, metal semiconductor and as well the PN junction in bias. I have done that here.
Okay, fine, fine. So we'll just like
Yeah, let's
try
see.
to solve. Yeah, yeah.
Little getting little bit in the sense a little bit complex. Yeah, I think it
Yeah,
needs little bit of good thorough reading a couple of times before you get that perfection and hand holding. Yeah.
yeah. So anyway, let us start
Yeah,
today's
let's
problem.
start. I think let's see how
Yeah.
fair I can
So
do.
let us move on to today's problems. So this is the first statement. Like which of the following statement is true regarding a metal semiconductor junction?
Metal and semiconductor.
Semiconductor
Okay.
junction. So you know that it
Five
can
is the
form
work
between,
function.
yeah, metal and p type, metal and n type, and depending on
Yeah.
their work function, it can be Schottky or ohmic,
Short
right?
Pyramic, correct.
Yeah,
Yeah, yeah. Well, you want
yeah,
me to answer this, right? Which of
yeah,
the
yeah.
following here to the junction is always ohmic when the semiconductor is p-type. Junction is always Schottky when the semiconductor is n-type. The junction is ohmic when the phi of the metal is greater than the phi of the n-type semiconductor. Junction is Schottky when phi of the metal is greater than the phi of the n times A character. D is correct.
Okay.
And
Like
C
A and B are wrong. You can like directly say because whether it is p type or n type, it
yeah,
can
yeah.
form both,
It's
right?
for both. Yeah, I know.
So these are wrong.
The C is what I'm looking. Junction is ohmic when the phi of the metal is
Yeah, you can
greater
check your
than.
notes, or if you have the textbook with
Yeah,
you, you can
just
check.
imagining. 1 second.
Yeah, yeah, sure,
Yeah,
sure.
just give me a
Yeah,
few
sure.
seconds to probably. Yeah, D is correct.
Okay.
C is not. Yeah.
Yeah. So these are the things you'll have to memorize. Like suppose it's a junction between a metal and an
Yeah,
N
this
type.
metal and yeah,
Yeah,
ohmic. This I know, but
yeah.
wanted to understand the junction is always ohmic. I wanted to understand even if it's N type or a P type, the work function of the metal is greater than the P type semiconductor, right? The same thing applies for the
N
D
and
one
P.
also, right? N and P, whatever it is.
Okay.
Consider okay. Let me read this. Consider
Yeah.
the junction between the metal and an type semiconductor. In here, it is okay. Schottky junction is great. QM is greater than Q semi in the Schottky, and it is okay. Reverse in the P type. What?
P type.
Okay.
Yeah. Yeah.
This I thought it was the other way around. Even if it is P type, the metal is stronger, is what I was thinking, but
Okay.
not because
It's the
okay.
reverse. Like what
Reverse.
these things will be
Here
reversed
the
here.
holes are transacting and here the
Electrons are.
electrons are transacting. But wanted to imagine how will be a Schottky junction for a p-type semiconductor. In that the electrons are higher in the metal.
Yeah.
In the p-type semiconductor it's the holes, right?
Yeah.
So
Suppose yeah, this is the case.
mm,
Then what happens is that
yeah,
your metal will be something like this. Right here is the Fermi level of the metal, right?
correct.
And your semiconductor will be like this,
Yeah, this is semiconductor, and you will have the
somewhere
valence.
here,
Yeah, you will have.
the Fermi level somewhere there.
Yeah,
Yeah.
in the.
So based on whether this particular phi m is
Mm,
above this for EP, let me call it EPI Fermi level, EPF. Whether it
mm.
is higher or lower, there will be movement from higher potential to lower potential, right?
Correct.
Yeah. So
So,
based on that, the
mm,
bands will bend. Like these two bands will bend. So that is how we arrive at this.
yeah, bands will bend, I'm sure.
Yeah.
But what will be moving? I am assuming the holes will have to move, right?
Yeah, like electrons move from
Uh,
higher to lower, so holes will be in the
correct.
reverse, right?
Sorry, come again.
If electrons move from the higher potential to lower
Lower
potentials,
potential. Yeah,
suppose you have a Fermi level here, and you have an electron here. This is the direction in which electrons
correct.
are
It will
moving.
move. Yeah, but how
So
will the
holes
holes?
will move in the opposite.
So opposite when you say there
Yeah,
are more holes on the p side conductor, correct?
yeah,
P side semiconductor.
yeah.
So the holes will move to the metal. That's what you're trying to say?
Yeah, like as you see here, here there are more like electrons are here, right?
Correct.
So there will be a movement like this.
Electrons will move here
Yeah,
also.
so
Hmm.
holes, like we are trying to understand with respect to electrons, but we will say in terms of holes. If electrons move in that direction, holes obviously will move in this direction, straight across the reverse potential. Yeah.
Can you explain this to me?
Yeah, can you
In the
like
P.
can you take a piece of paper and try drawing that? Like,
Yeah, yeah, I'll do that.
yeah. You can just start like that. So then I can help you. Like how, suppose I can draw this condition. So there is a metal, there is a p-type semiconductor, and phi m is greater than
Yeah,
the work
let give me a
function.
moment. I'll get
Yeah,
the
sure,
paper
sure,
handy.
sure.
Yeah, sorry.
Yeah.
Um, I am doing metal and which is
P-type
P. Oh,
metal and
metal is always
yeah,
metal, right? It
and
cannot be P.
no,
Yeah.
no, I meant metal and p-type semiconductor.
Metal and P type.
Yeah,
Okay, metal and a P type semiconductor. Okay. And the P type,
and
the
phi m is
Fermi
less than
level
5 semi. Yeah,
5 m is less than 5 semi. So 5 m is less than 5 semi when you mean the work function of the metal is less.
yeah,
Correct, yeah. So it's here more electrons on the metal
yeah.
and less
Electrons in the
electrons
semiconductor
on the
state.
semiconductor. Correct.
So electrons will
So
start
electrons
migrating
will move from metal to the
semiconductor.
semiconductor. Correct.
And what happens is that because of that there will be a positive potential on the metal and a negative potential towards the semiconductor.
Correct.
And
Positive on this,
yeah,
negative on this. Correct.
and then
And the
what
bands
happens is
align.
bands will bend upward in the direction of field.
Field. So
Yeah,
field will move from positive to negative. So
yeah,
it will move like this. Okay,
from
correct.
metal to the semiconductor.
Metal to the semiconductor. Okay.
Yeah,
Um. Okay, that's how it behaves. That's
yeah,
I was thinking Schottky is only when I was thinking mm so in case of N type, what happens now is it happens the other way around, right?
yes,
The QM is greater. So semiconductor electrons move from the semiconductor to the metal,
towards the
correct?
metal. Yes.
Correct. Okay, okay, okay. Okay,
Yeah. So,
got it.
like
So this,
for all types, whatever combinations we are taking, the electron migration and how the field works
mm,
and why the bends, like bands bend up, they remain the same. Only the names keep changing.
okay, yeah, this we have to remember.
Yeah.
I think this was not there in the video and the textbook also, the
Okay.
P type. So I was confused. I was thinking always that you will have some material, whereas the QM is greater than the Q semi, and it might always depend like that. You'll choose a material wherein for doing a short key wherein QM is
Oh,
always greater than. That's what I was thinking. But yeah, it's reverse for the P type.
yeah.
Okay, thanks
Yeah.
for clarifying.
Okay.
Yeah.
So this is the next one. Junction, like you
A
have the
junction.
image with you, right? Like same way you have just drawn right now, you can
Yeah,
draw
yeah, I'll
it
do
in
that.
N type. Yeah.
I'll do that. A junction is formed between a metal and an n-type semiconductor. The work function of the metal is this much. The electron affinity of the and the band gap for the semiconductor is for What is the Schottky barrier of this junction? Give your answer in V volts, right? Okay.
Yeah.
So I'll draw a Schottky junction with the N type, right? So
Yes.
in this case, the phi m is greater than the semi. So yes, this is the Fermi level, and this is the
Like you can draw
semiconductor.
the image for what happens after the junction has formed. Now the separate ones, and first you can draw an image for like at equilibrium what happens, and after the
Yeah,
motion of electrons, they'll form a junction, right?
correct. Yes,
Yeah.
they'll
So
form a
the
junction.
second, yeah, from
Uh,
that you will get an idea of what is 5D.
the work function of a metal is 5.5 eV. So yeah, this is more like in Fermi level. It is more of from Fermi level to the end. Okay, 5.5 eV. Okay, the electron affinity and the band gap of a semiconductor is band gap is 1.3 eV. Okay, there is a band gap, and then there is a conduction band. So valence band. Um, Here the bands bend from semiconductor to the metal.
Metal. Yeah.
So bands bend in the upward direction
Yes. Yeah.
from like this. Okay, and I get a phi b of the electron affinity. Band gap is 1.3. Okay, 1.3, and electron affinity is okay this much. That is 4.0. So what are they asking respectively? What is the Schottky barrier
Barrier. Yeah.
of this junction? Okay, short. You have to do that equation, I think, right? There is a equation.
Like you can use
Yeah, you can
what
equate, but
can
I
you
think
use there?
without that you can do that. One second. The Schottky barrier is the difference between the metal and the Qm minus work function of the semiconductor and difference between the work function of the semiconductor and the metal, right? So in this case, it is.
No, like that is EV0. That is the built-in potential that happens. Phi m minus phi m is EV0. Like
Okay.
short key barrier is 5B. So
Yeah, 5B. So
yeah,
what is the formula for the 5B?
it is phi m minus psi n
Ah, phi m minus,
minus
yeah,
psi.
there, psi n. Okay, phi m is 5.5 and psi n is 4.0, correct?
Yeah,
So it is 1.5
yeah.
electron volts. So you have to convert it to voltage, right?
Need
Volts.
not be like yeah,
You
you
were
can
answering
yeah,
volts, no?
volt. Then you can convert. Yeah.
So you have to multiply 1.5 into 1.6 into 10 raised to 9.
No, no. I think here it's actually electron volt because those are different. They're not the same thing, right? Like voltage,
Yeah,
yeah, electron
yeah.
volts in terms of energy. So this has to be electron volt. Yeah. So no conversions are required.
Yeah, electron volt is energy
Yeah.
and voltage is it's a potential. Yeah.
Yeah.
Okay, yeah. I think yeah, good.
And
Thank you. I
yeah, and
learned
one
something.
more thing you can do is like this phi b we write as psi m, sorry, phi m minus psi n, right? One
Hmm.
thing we can like otherwise uses phi m minus phi n
Plus
plus ec
psi e
minus
minus
efn.
yeah.
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 So this altogether gives us the psi n part.
Yeah,
Yeah. So
got it.
in questions where the electron affinity is not given and all the rest are there, you
Uh,
can try that.
yeah, we can try that. I think we have to draw the band
Band
diagram
gap.
correctly.
Yes. Yes.
Yeah,
All
that's
the
where
time
the
it will
whole
help.
whole whole crux is in drawing the correct band
Band
diagram.
gap.
Yeah,
Yeah.
yeah, got it. Yeah. Okay, thanks. Next. In a PN junction, what is the relation between the built-in potential and the Fermi level? In the P and the N side, okay, in the PN junction, what is the relation between the built-in potential and the Fermi levels in the P and the N side before the junction is formed? Take the reference for the Fermi level to be the top of the vacuum level for both the
P and N sides.
Oh, they are asking us to take the Fermi level to be the top of the vacuum level as the Fermi level. That's
Yeah.
what they're saying. Okay, let me
That is
draw.
after formation. Yeah, you can draw it
Yeah,
after formation as well.
but they are asking the question in a PN junction: what is the relation between the
Between
built-in
built-in
potential
potential
and
and the Fermi level.
uh, the P and the N sides before the junction is formed? Okay,
Okay.
before the junction
Potential
is
Fermi.
formed, they
Yeah.
are asking. Okay,
Okay.
yeah. Give me a moment. I'll just draw this. Okay, I draw that. The relation between the built-in potential. So I think we can do it from the equation.
Uh, yeah, if you like remember from the equation, then it's fine. Otherwise, if you remember, there would be another diagram like this, right? Like what happens
Yeah, but
post.
they are asking us to do the what is the relation between the built-in potential and the Fermi level in a P and the N sides before the junction is formed.
Yeah.
Before the junction is formed, built-in potential is something which happens when the both P and N junctions are formed, the
Yes.
joined together. When they are joined, the built-in potential increases, right?
Yes. Like it forms
Yeah,
a depletion region in between the two.
yeah,
The Fermi levels
yeah.
will start lining up, and once the Fermi levels have lined up at equilibrium, like which of these
Correct.
statements you are correct, you can check.
Okay,
Yeah.
both built-in potential is the sum of the Fermi levels of the N and the P side. Built-in potential is the average of the Fermi levels and the built-in difference of the Fermi levels. Oh, one second. Let me
Yeah. Sure.
draw it. I think it's a little bit. Is it A? It's either A or
Are you sure?
C. A or C. I'm
C
not
is
able
the
to
answer. Yeah.
see A or C. I'm not able to visualize. Can you just explain me a little bit on this?
The screen is not showing.
I can see your screen, I think.
Okay.
Yeah, I can see your screen, but I'm not able. Yeah,
So this is basically before the junction forms, right? So P Fermi level will be here, N Fermi level will be here, more electrons are there, so electrons
yeah,
move
yeah.
from here to
Mm,
here.
mm,
So
mm.
hence positive potential here, negative potential here. So field will be like this.
Field will be in this direction,
Yeah.
correct? Yeah.
And what happens is bands will bend up in the direction of the field, right?
Hmm,
Yeah. So this
hmm,
is
hmm.
finally what happens.
Yes.
So across the junction, like once they have lined up, we need to find out between vacuum and what is between EC. That is the built-in potential that forms.
Come again. Between.
Between the top of EC, not vacuum, between the top of the like
Hmm. Hmm. Hmm.
EC, that is the conduction band potential, and here. So what is the difference between, like how much does the band bend up basically?
Correct.
Yeah, so that is the built-in potential.
Okay.
Yeah, like
Okay. 5p minus
minus 5n.
5n.
That is this much minus this much. That is that particular, the small difference is there, right? This particular difference.
Correct. Correct.
This is the
Yeah.
amount by which the band bends up.
Correct.
Yeah,
That's
that
true.
is
Can you
because
come to the options there?
yeah, that is
Yeah.
because EP and EFN has to come at the same level at equilibrium, right?
Correct. Correct.
Yeah, so
Correct.
that is the difference that they have to bend up.
Uh,
Yeah,
C, right?
yeah,
In built-in
difference
potential is
between
a different. Okay, just come again to the second picture, the second page. Yeah, you just showed. No? Yeah, this. So it has to move by 5p minus 5n. 5n is this. Uh, yeah, correct. That's true.
the small
It's too
detail.
much to visualize. Yeah, too much to visualize, but they should give this diagram probably and tell us to visualize. Otherwise, drawing it is a little bit tricky. I don't know. I have to practice that probably. Yeah. Okay, I will read this. A junction is formed between a metal and an N-type semiconductor. The work function of the metal is this much. The electron affinity and the bandgap of the is this much. What is the Schottky barrier of this junction? I think we just did this, right?
Yeah, the same thing.
Yeah,
How
same thing.
much
I
will
think
be the
it
value?
six. The work function is 6.1 minus 1.3, 4.8 probably.
Yeah, this is like electron affinity is 3.6.
Okay, 3.6. Sorry, yeah,
Yeah,
3.6.
so it will be 2.5.
Yeah. Okay, so you have to remember this. Okay, got it. Consider N-type silicon. There are 26 questions I saw somewhere. So we are on the fifth. That's how much we take time.
26, I don't think there are 26.
Okay, no problem. Let's take it at the time.
Like you
And
can
have you uploaded the last week's?
PPT. Like the thing is, our drive is down, so it
Yeah,
will
I
get
could not
yeah.
find it. Yeah.
Like the students are not able to upload anything towards the IIT and Google Drive. So I've asked them
Uh,
for help, and till now it's not rectified. So it might
okay.
take some time. In the meantime, if you want, if you post your mail ID here, I can share it to you personally.
Yeah, I'll do that right away.
Yeah.
1 second. Where do I? Where is this message writing? Okay, here. I'll just type it.
And the equations sheet too, I can mail
Yeah,
it.
please do that. Yeah,
Yeah,
that'll
and the
help
thing
me.
is, I'll confirm with sir whether the same equation sheet is there for exam, and if there is an updated version, I'll send that. Otherwise, this will
Yeah,
be the one.
sure, sure. That should help me.
Yeah, I can mail it, and like, yeah, I can attach the PPT to this one. Yeah.
Yeah,
Like, and in this question, like, take a fresh
you
sheet
can
and try
also.
noting down all the values, and then you'll have to
Yeah,
draw the diagram again to
yeah. We
visualize.
have to draw it ourselves. I think that
Yeah.
is where. Yeah, you can send me on this. Perfect. I'll we'll do the fifth one. Consider a N-type semiconductor with 10 raised to 17 donors per centimeter cube. The electron affinity of silicon is 4.01, and the work function of the four potential metals for contacts are as follows. This choose the correct statement regarding the work function of the N-type silicon and its type of contact when the metal T is equal to 300 Kelvin. Okay, got it. Um, okay, let me
Yeah,
just
you
draw
can.
the, yeah.
Or you can try solving the first part to get Fermi level, and then if you compare the values and remember the like how when ohmic and when Schottky is formed, you can try that way as well. That is easier than drawing the diagrams, I guess.
Yeah,
But
yeah, I
yeah,
think I was trying to do that only, not drawing the diagram, but when Schottky's, and because this is an N-type semiconductor,
yeah,
so Schottky is formed when phi m is greater than phi m is
greater than,
smaller,
yeah,
small work function is greater, right?
work
Phi
function is
m is
greater than the
phi m
semiconductor.
is greater than phi semi.
Yeah,
It is Schottky, and the other way around is
ohmic junction.
phi ohmic junction. Yeah. So this we can solve, right?
Yeah, yeah. So first, if you get phi n for the semiconductor, based on that we can say. Yeah.
The electronic affinity of silicon is 4.1,
Mhm.
4.01,
Yeah.
and you need plus Fermi level for this.
Yeah. So Fermi
Uh,
level value we'll have to solve using the equation that we learned in previous weeks.
for silicon, take EG, they have already given. No,
Yeah.
EG is 1.10, so divided by 2. 1.10 is
No, that is for an
that is for
intrinsic.
a
Yeah.
intrinsic. Okay, okay. This we have to solve
So
for getting the.
Fermi level.
Okay, what equation do we have to? EFI minus EFN, EF that half.
Yeah. EFN minus EFI is equal to KVLN. That
Mm,
part. Yeah.
mm. So that equation we have to use and find the
Yes.
Fermi level and then add that here to get the work function of the
Yeah.
semiconductor,
And
and then the work functions of the metals are given here.
given. And one more thing is you have n value here. That is sorry, n, we call it nd usually. This is
Yeah,
an
it is
n type carrier, and here we
fully
have n.
ionized.
Yeah. And this is ni. So we will have to take two equations for that, and then take their
Difference.
yeah. Only then you will be able to get EFN.
Okay,
Yeah.
got it. Yeah.
Can you try?
So I don't know the equations now. I have to really go back and scout that. If you
Okay.
can,
So I think I can show you the equation.
yeah, show me the equation. I think that should be fine. I should go ahead and practice this only, then it'll happen.
So this is the equation sheet.
Okay. So I have to choose.
It's directly given here. Don't
Yeah,
you?
EFI is equal to EG by 2.
Not that one.
No, not that. The EFI is equal to
You have n and ni. So
NNI. Yeah, is the EFN minus EFI is
yeah,
equal to KBT.
ln n by
Uh,
ni.
yeah.
This one.
So yeah. So EF.
So can you just note it down and try solving for it?
Yeah, I'll do that. I'll do that. Yeah,
Yeah.
1 second. Let me note this down. EFN minus EFI is equal to KBT ln of N upon Ni. Yeah, just go back to the question, please. I noted down this, so thank you so much. The NF semiconductor is Na is sorry, Nd is
N.
10 raised to 17.
Yeah. That is n basically n.
N, yeah, this is N is equal to N. So Np is equal to Ni square divided by Nd, correct?
Yeah.
So Ni square is 10 raised to 10 the whole square. And that is 10 raised to 20 divided by
Was there a
Nt
square
is,
there?
yeah, there is a square, no? Ni square you have to do, right? Ni square, right? You have to do that.
No.
No, I'm not, Ni square is not there, but if you have to take n, uh,
Yeah.
oh no, Ni is directly
Yeah.
in that. Okay,
We,
oh, okay. You don't need to do an NP. Okay, got it. EFN minus EFI is equal to KBT into KBT value. They'll give this value, right?
yeah.
KB value. in electron volts. What is that if you can give me?
Here you have kb.
kb is
It is
1.38
in joules per Kelvin.
into 10 raised to minus
23.
23 joules per Kelvin. Yeah, we use this only, right? Most of the time.
Yeah, but then you'll have to convert your electron volt values into joules as well. Like
Oh,
if
this
you,
we can convert into electron volt, right? We have to
yeah,
multiply into 1.6 into 10 raised to minus 19.
yeah. So better like you can convert maybe the 0.55 values. That would be better. 0.55 into 1.6 into 10 power minus 19 if you take. You
Yeah,
can
that's
use
one.
kb, yeah, directly.
You have to multiply, right? By 1.6 into 10 raised to minus 19.
Yeah, for the
Convert
electron
into
volt value, whatever is there in your band gap value, same thing.
uh, sorry.
I'll show it. So here, like you have your EFI in 0.55, right?
EF, where is EFI?
Like the
Yeah,
temperature.
EFI is 0.55. Yeah,
Huh,
EV it is.
yeah, if you multiply that value to 1.6 into 10 power minus 19, it gets converted to joules, right?
Mm,
Yeah, electron volt into joules.
yeah, correct.
Yeah,
Yes.
so then you can substitute.
Okay. Otherwise, I can do the other way around. No, I
Yeah,
can
then
just multiply
okay,
1.38 into 10 raised to 19 into 1 point. If you can show that sheet,
yeah,
please. Sorry, I know it's difficult to switch.
yeah, it's okay.
Yeah, if I multiply 1.38 into 10 raised to minus 13 into 1.6 into 10 raised to minus 19, then it is in
No,
EV, right?
like if electron volt is converted to joule by multiplication. If you want to convert the reverse, you'll have to divide this 1.38 into 10 power minus 23 by 1.6 into 10 power minus 19.
Oh, okay,
Yeah.
okay,
So
okay, got
better
it.
to multiply than divide. For me, at least, I do that.
Okay. So you are telling I have to multiply this with 1.6 into 10 raised to minus 19 to get it into joules,
No,
correct?
yeah,
Multiply the EV into joules.
yeah.
But what is that answer they're asking in EV, right? Then again you have to divide
Okay.
the,
The final
right?
bit. Okay, then
Yeah,
maybe you can do
fine.
the reverse.
Yeah. So I'll just convert this, no? It
Yeah,
should
fine.
1.38 divided by into 10 raised to minus 23 divided by 1.6 into 10 raised to minus 19. This is in EV now, correct?
Yeah,
I'll use this virtual calculator. Just give me a moment.
yeah, sure.
And also, if they give us to use a normal calculator, that will be very helpful.
Helpful, yeah, but I don't think that will be allowed. If you divide it, you'll get an electron volt and then you can solve.
Okay, I forgot this. How to do raise to 10 x raised to y you have to do, or it is e raised to x.
It
10 raised to x. Sorry, yeah,
10
I
raised
got
to
this.
x.
10 raised to x, and I do it minus 23. That's it, right? Minus 23.
Or you can just do the decimal places and 10 power minus 23 and minus 19, you can just do it manually. It will not.
Yeah, I can cancel it out, right?
Yeah.
Both will cancel. Yeah. 38 into 10 raised to 10 raised to minus 4. Okay. Yeah, I'll do that. That works better. So how did you say that 10 raised to x raised to y? How do I do that? 10 raised to minus 4 if I have to do.
Yeah.
You said something, right? I have to choose 10 raised to x and then choose minus 23.
Yeah.
Minus 4.
Let
Minus
me
4.
let me take the virtual.
Something I'm
Maybe,
doing
and
wrong.
there is an app like you can download on your phone. Like for ease next time, maybe you can try that. You need 10 to 10 to the power minus 23, right?
No, I want 10 raised to minus 4 now directly. I'll
Okay.
multiply. I have done that math. So 10 raised to minus 4, just show me if you can pull in your.
Like you type minus 4 first and then you press 10 to the power x.
Okay, minus 4 first. Okay,
Yeah.
minus 4 first and then 10 to the power x. Oh, something went wrong. It didn't take minus 4. Okay, minus 4. No, it is not
Um,
something I'm trying.
like you have to press after like minus
Minus 4 I'm
4.
placing first.
Yeah.
Yeah, and then 10 raised to x.
Minus 4 first you have to press the equal, then only it will. Then you have to press 10 to the power x.
Minus 4
Then equals,
equals. Okay,
then
then
10
in.
to the power x.
Okay, into point 0.086.
0.086, yeah. That,
No, 0.86. Yeah,
yeah.
0.86, not 0.86. So it is yeah, I got that answer now. Point. Okay, one second. In doing this, I forgot the major what I had to do. Okay, got it now.
Temperature is 300
Now
Kelvin. Yeah.
300 Kelvin. Okay, so I got this KBT now done. So point 0.086 into ln of n upon ni. N is 10 raised to
Into
17 divided by 10 raised to 10. So yeah, so now it is 10 raised to 7. Ln of 10 raised to 7, correct? Yeah.
yeah.
Ln of, how do I do ln? LAN I have.
And
LAN.
since you're using the virtual
Uh,
calculator, you can do it step by step instead of a single go. Like,
yeah, I know, I know.
yeah,
Yeah, I'm doing step by step only now. 10 raised to x raised to y is that right? 10 raised to,
uh,
yeah, 10 raised to 7. Yeah, I got it. This is right, I think. In LAN of, then LAN, yeah. LAN is 16.11.
yeah, 16.1.
16.11 into this, into
300
T. Yeah,
into, yeah,
T, yeah.
K. Yeah.
Into 300 into. It is 0.415.
Now you need,
EFN minus EF.
okay,
EFN. Yeah, I have to do that now. Okay. EFN minus EFI is equal to 0.4158. Okay. Now what do I need to do? Can you come to that
yeah.
question?
So EFN is done, right?
Yeah, EFN
Point
minus
nine.
EFI is done. So EFN I have to find.
Yeah. You mentioned
EFN is equal to.
you have to add both the things, and you just mentioned you point 0.4 plus point 0.5. Obviously, your answer is correct. It's like point 0.9 something something.
Just come to the question. Sorry.
Yeah.
What are we trying to find? I missed that.
Like
Uh,
whether Schottky or
okay,
junctions
okay,
are
yeah, yeah,
common.
correct. Okay. So now we are trying to find out phi and phi of semiconductor, correct?
Yes, yes.
Okay. Phi of semiconductor is nothing but your affinity plus Fermi level. That is EF n, correct?
Yeah.
So EFI, I know it is 0.55. Okay. EFN is equal to this much, point.
So this is the work function that we need.
Okay, correct.
For example, try. This is EFN. So this is your conduction band. Sorry, valence band, and this was your conduction band.
Correct.
You need to find phi n. So this much.
Phi n, yes, correct.
Yeah. You
So
have.
phi n is
Yeah.
EFN plus that affinity.
Yeah.
Yeah, correct. EG. Okay, this EG I missed that. EG minus EFN.
Yeah.
Why is EG? EG is half you have to take,
Yeah,
no?
AG is
That is
half. So this much you need to remove from your calculation. That is why you take E. This is suppose EG minus EFN means this much would be gone, right? We need only from here.
correct. So why in the equation here I see that EFG minus EFN. It should be EG minus divided by 2, right? Here, the one you're showing here on the screen. The one marked double line.
Like here you're asking.
Yeah, 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 yeah.
Okay. You're asking whether it should be EG by 2.
Correct.
Okay, let me think. This whole thing is EG and this much is EG by 2.
Correct.
Okay, your
So it
EG
mm,
minus EFN.
your EFN you want to find out,
Yeah,
right? EFN to the affinity is your work function of the semiconductor, correct?
yeah,
So now you have EFI is a 0.55 in an intrinsic semiconductor.
conductor. Yeah,
So you for finding EFN you did you just add EFI plus that value,
yeah.
clan of
This
whatever you got.
much. Yeah.
Yeah, point I got it
This is
something,
your
right?
EG and this
0.145.
is, yeah,
Yeah.
this small, like this entire thing is your EG. EG.
Hmm,
This entire thing is EG, and if whatever EFN, everything we are taking with respect to the valence band, that is taken as 0.
correct.
Yeah. Then EG minus, this is your EFN part, whatever you calculated just now. So the small region you have got now. That plus your psi will give you the work function, right?
So you have to your psi is EFN plus that psi, correct? You have to find EFN. That's what I'm trying to say.
Like EFN, we have already completed. Let me draw once more.
No, no, I'm from the equation standpoint I'm talking.
Okay.
So I don't draw. I think see here. You
Okay.
got EFN how much? It is 0.55 plus
Yeah.
plus 0.451, yeah, point 0.9 something you'll
Yeah.
get. EFN you got, right?
Yeah.
Now if you add EFN plus XN, XN is already given to you, right?
Yes.
In your solution.
Yeah.
So what is that? Just get that XN.
It is 4.01.
4.01 plus zero point 0.9 0.967 is your phi n, correct?
No, like this is because this is 0. Let us take as valence band edge is
Hmm.
0.
Hmm.
Now, if the thing that you want is phi, I see that is
N,
phi n. Okay, this is phi n.
correct. So
Now,
phi is something from EFN, right?
so this was
EFN.
just EFN. EFN.
Okay,
And this is psi.
exactly.
Yeah, if you add those things, you're not accounting for this part, right? The small part.
Okay,
Yeah.
okay. That is your. So how do I get that
So
now?
now they have given that the whole thing, this entire thing is EG.
Correct. EG, correct.
And if you subtract whatever EFN you got from that, you are accounting for the small region. Like EG minus EFN means the small part.
Correct. Okay. From
And then
there to
if
plus
you add your
XN.
psi in, you will get your phi.
Okay,
Yeah.
okay. Yeah, it's N type, so it'll be up. Okay,
Yeah.
got it. Perfect. Yeah, thanks. Yeah,
Yeah.
you're right.
Yeah. And now you have your phi in, right? Now you can
Yeah.
compare that with whatever is
With
given for
yeah,
different
short key or
methods.
yeah, got it. Yeah,
Yeah,
yeah.
that's all.
Oh, this is going to take a lot of time in
Time,
the
yeah.
exam to solve. How many hours is this exam? 3 hours
3, I
or
guess. Yeah.
Okay.
So now, if like you see there, and now like, based on 4.14, can you see the question and tell me what is Schottky and what is omic?
Yeah. Uh, uh, phi n should be larger, right? So if you can just
Whether
yeah,
this
this one, next one. Yeah, phi n is 4 point. How much you said?
1 4.
4.14.
Yeah. So you have
So
this
I
or
have
this.
CS is 1.8, 2.5,
1.8 and 2.5.
2.5.
Yeah.
Lithium or CS, right?
Yeah.
Either of them.
Yeah.
So how do I, if there are two options,
If your phi m in that if in case of CS and lithium, your phi metal is less than your phi semiconductor, right?
Phi
Phi,
metal.
yeah, metal, this like cesium or lithium, whatever they are giving is the 5M.
Correct, correct, correct. That is
So
less, no? Yeah,
1.8 or 2.5 is less than 4.14. So
correct. So
will
you
that be
should have
short?
something.
Yeah,
No, no, no,
yeah.
not yeah.
Now is it Schottky or ohmic when it is lesser?
Correct.
Yeah. So is it ohmic or Schottky? From the first question, if you remember, if 5M is less than,
No, in short key, it is 5m is greater,
okay,
and 5m is greater than your phi of n-type semiconductor.
yeah, greater. So then this
So
would be
short.
the answer, right? Because in case of aluminium, it's 4.25 and it is 5. So 5 metal is greater than 4.1 for whatever we got.
Correct,
So
correct.
aluminium and gold forms Schottky junction, while cesium and lithium forms
Oh, okay, huh,
ohmic
okay.
junctions.
Ohmic junction. Yeah, perfect.
Yeah.
Yeah, thanks. A lot of confusion.
Like,
Yeah, I think I'm getting clarified. Yeah.
yeah, these things you'll have to memorize. Like which forms
Yeah,
contain.
that I can
Yeah,
memorize.
yeah.
Yeah, this I remember now over the period of time. I think if I read another time, I should be able to memorize this. Yeah, thanks. I think this is
So next is there is a silicon p-n
silicon
junction.
PN junction found with a donor and acceptance concentration of 10 raised to 16. If the intrinsic carrier concentration of what is the built-in
Potential.
potential of this junction? Is it an equation? I can
Yeah,
direct
yeah.
substitution. I think there is an
It's a direct
equation.
equation. Built-in potential, if you see,
Where is that? V naught, right?
yeah, you need V naught.
Yeah, where is that V naught? I'm not able to see that.
Have you found it?
J is there.
Yeah, and
One
next
second.
next line to that. P-n junction contact potential V0.
V naught,
Yeah.
yes. KBT. Here is that only, 1 point
E value is given 1.6 into 10 power minus 19. That is
minus
charge of
19.
the
Yeah,
electron.
yeah. And come down in that equation, there are few values.
KBT
N is KBT. I got this. This is very simple. Ni square is nothing but your intrinsic square. N is your
n-type carrier
uh,
and p-type carrier.
N type carrier in the N side,
Yeah.
and PP is your P whole concentration
With
in the
P
P
side,
side,
yeah.
correct?
Yeah. If you
Yeah,
note
okay,
down,
yeah.
it's a direct
Yeah,
substitution. Have you noted down?
direct sub. Yeah, I've noted down. You want me to solve this?
Yeah.
Yeah, I'll do that. Yeah, I'll do that. Just need note down. Let me just show that equation once. And NPP divided by
NI
Ni
square.
square. Yeah. So KBT is equal to, give me that. So can you put that in electron volts also? That'll help a lot actually.
Um, Here, I think you will have to give your final answer. You have to give in volts, right?
Yeah, in volts. So
Yeah.
you have to put it in joules then, right?
Yeah. So you can use your
Kb and
Boltzmann constant directly, 1.38 into 10 to the power minus 23 directly you can use it.
138 into 10 raised to power
Minus
minus
23.
23
No conversions
divided
are
by,
there.
okay, divided by E is 1.6
Yeah. 10
E
to the
value
power minus 90.
into 10 raised to power minus 19. Ln of n is it is 10 raised to 16, right?
Yeah.
Acceptor is also
10 to the power
10 raised to
16.
10 16, and this is also the same 10 raised to 16 divided by 10 raised to 20, correct?
Yeah.
Yeah, I'll just solve this. Yeah, I'm there.
Yeah.
I'm just solving it. Yeah. Is it 976 volts? I think something is wrong. I think
Yeah, like
some
it's not there with the options, right? Where have you gone wrong?
think something I did wrong in the LAN thing.
Okay.
Yeah, this right. 10
Mm.
raised to 16 into 10 raised to 16. Yes, 10 raised to 20.
10 raised to
Uh,
32.
oh, I have not multiplied by 300. Okay. 300 I divide. Okay, this I have not done. Multiplication of 300 I have not done.
So that would be
Yeah.
around like point 0.7 something.
Yeah, just explain this EV to that conversion, no? Joules. 1.38 into 10 raised to minus
Like
23 is
electron volt,
per
if you
joule
have,
per Kelvin, right?
so 1 electron volt into 1.6 into 10 to the power minus 19 will give you joules. So
Okay,
that is
joules, correct.
1 electron volt is 1.6 into 10 to the power minus 19 joules.
Joules, okay.
If you want to do the reverse, so then if you want to say 1 joule, it would be 1 by 1.6 into 10 to the power minus 19 electron volts.
Okay,
Yeah.
correct, yeah. Okay. So you have to multiply this 1.8 divided by, okay,
Like,
1.6 into.
like here, no conversions are required. This E is actually this thing. Yeah,
Mm-hmm.
like here you are using K directly. No conversions are there since it's asked in
So
rules.
this will give no uh, volts, right?
And this is
It's
a ratio, so it doesn't matter.
okay.
Like if it wasn't a ratio, then in order to get volts, you have to convert the centimeter into meters in any
Okay.
kind of equation.
Hmm. Yeah, I think I should do it better on the calculator. Okay. Consider Schottky junction diode between gold
Yeah.
and N-type semiconductor with 10 to 6 donors. The electron affinity of silicon is this, and the work function of take Ni is equal to the band gap of silicon. Assume incident. What is the built-in potential? I
But
think this also is a substitution.
but
Get
in before doing the substitution, we need something.
mm,
Yeah. Because if you see, like we need the final thing that we need is EV0, right?
yeah, EV not we
Yeah.
need what
And
built-in pot V not right?
mm,
EV not or EV not?
EV naught, like or
EV not, yeah,
basically,
yeah.
or let's say that we need EV naught. Here you can't use the equation that you used before, right? Because that was based on Ni, Nd, Np, and all those things.
Correct.
So here it's a Schottky junction. So first you will have to draw the junction, and then using this psi, Eg, Ef, Efn,
Uh,
all those
uh,
things, you have to find this one.
okay.
Yeah. So it is like what the work function is given for the metal and then get, yeah. So it's a Schottky junction. So 5 metal will be greater than or less than 5 semiconductor. If you remember,
Schottky junction is 5 metal will be greater than
greater 5 metal will be
semi
greater than 5
5
semiconductor.
semiconductor.
Yeah,
Yes, yeah.
5 semiconductor. So this is
Mm,
like what 5 electron volts, right? So now you
mm.
can try drawing the case like how the final junction would be. 5 metal greater than 5 Se if you remember. And yeah,
Yeah, but they're asking us to
right?
calculate the built-in
Built-in
potential.
potential. We don't have a
Yeah.
direct equation for that.
So what is missing in the equation? If I get to know that, then I'll
Yeah,
be able to find out.
yeah. And in order to get that, you will need the like in the bending what happens that diagram you need. For example, if this is the case, then you have something like this, and
Mm,
then this here, like something
Mm,
like this would form finely, right?
no, no, no. Other way around, no.
Is it? It is Schottky junction, right?
Yeah, short key. That's what, no.
Yeah,
Phi
5m
m.
greater.
So phi m greater. So
Yeah,
you
after
should move.
equilibrium. I'm drawing after
Yeah,
equilibrium.
after equilibrium also, no.
No, after
Any
equilibrium, the Fermi levels will come at the same level.
correct, but the band should move from the field, right? Field to the
Yeah.
upward to the field. That
So
that band.
yeah, like phi m was greater than phi semiconductor. So electrons
Correct.
will move from here to here. So this was
No, no, no,
positive.
no, no.
This was
Phi m is greater. Electron will move from semiconductor. Phi m is greater means there are more electrons on the
okay.
semiconductor.
Yeah, true. Then it will move from here to here. This will
Here
be
to here,
plus
yeah.
and this will be minus.
Negative. So
So
it band should
semiconductor
bend from
bands will bend, like field will
like
move
this.
like this. So
Yes,
semiconductor bands will move like this.
exactly.
Yeah.
Yes.
So here it's yeah,
No, like this. Uh,
yeah,
bands will move in the direction of the
up in the
field
direction of
upward.
field.
Yeah.
Yeah.
Okay. Yeah.
So
Correct. Yeah.
SC
Correct. That's
bands move up in the direction of field. Your field is like this.
okay. Up in the direction of the
Field.
field. Yeah. This. Yeah.
So
Okay.
I think I'll have to draw it better.
No, no, that's fine. No problem. Go ahead. Go
Okay.
ahead.
This is the Fermi level after equilibrium. Then
This is your yeah. Correct.
and this is my 5D Schottky barrier.
For a Schottky barrier,
Yeah.
yes. And this
And
is
what I want is they are asking me for the built-in potential. Built-in potential
correct.
is basically this thing.
A built-in potential is that, no?
Yeah, EV0. These both are same. Like both of them are same.
Okay, both are okay.
That
Okay,
is
both are
phi
same.
m minus phi n.
So what are these dashed line you have drawn there? Both
Which one?
the above vacuum level and the between you have done, no? EV naught.
This one, this one.
The top two dashed lines. What are those?
This is the vacuum level.
Yeah, that is the vacuum level. The middle one. There you have drawn one, no?
This one.
Middle line,
This is
middle
the
dotted
Fermi.
line. That no. The next, the above that.
This one. No, that is I just mark the
Oh,
end
okay,
of
okay.
the
Mark
barrier.
the.
Yeah.
Oh, okay, okay, okay.
That
Got
is
it.
phi m minus phi n.
Okay, yeah.
Okay. So now they are asking for this V0.
Correct.
Yeah. So for that you need phi m and phi n. Right.
Phi m is given, no?
Phi m is given, but for phi n you should start with finding the Fermi level.
Okay, correct,
Yeah.
correct, correct. Okay. So we whatever we did in the last time, right?
Yes.
So that is
So using the equation separately, you'll have to start. For example, first they've given Ni is given to you, and what are their electron size there. Then Nc is equal to Nv is given. So
so Nc is equal to Nv, then you can directly use that 1.1, right?
yeah,
As Fermi level divided by 2 as a Fermi level.
can you? I
Yeah,
don't.
because Nc is equal to Nv, then you can use, right?
Yeah,
Your Fermi level in the intrinsic is that
but
much.
here the thing that we want is phi n, right?
Phi n,
Phi n,
correct.
yeah.
So
So phi n is basically then Ec minus EFN
plus
minus psi
Ec
minus
minus
EFN. Yeah, that is like think about a normal n-type semiconductor.
yeah plus sign, no?
Is it plus? Ah, yeah, plus psi. Yeah,
Yeah. Okay, I got it now. Yeah.
yeah. So now you need to start with finding these two, EC minus EFN. And for finding EC minus EFN, you can use the equation n like. Let me show you the equation sheet. EC minus EFN, we have something. EC minus EFN.
It is there. No, where is it? EC minus.
What's the top? No, they don't have it here. Yeah, like using intrinsic carrier concentration, if you see here, like the second line, useful relation second line, this the equation for Ni can be modified according to what we want.
Which one? Which one? Sorry.
Ni is equal to root of NCNB exponential minus Eg by 2 times KBT is there, right? Intrinsic yeah,
Correct.
semi.
Yeah. Interact. Yeah.
That thing you can modify.
So what do I modify it
Like
to?
actually, right? When I keep coming back, the screen gets,
No, that's fine. I can see your screen.
but the PPT is not visible, right?
Yeah, PPT is not visible now.
Take it as much.
Maybe you have to share your screen. I think you're sharing the PPT
Yeah,
alone.
yeah,
Just share the whole screen, then whatever you're sharing will just keep coming. Share screen you do instead of share the content.
content. Yeah.
I Now I can see your screen.
That's okay. So, like first part, we have kept this aside, right? Like phi m minus phi n is equal to EV0 from the like figure that we had drawn,
Mm,
and that
mm,
one you can
mm.
write as phi m minus plus
Well,
EC minus EFN minus psi n. Sorry, plus psi m, right?
yeah.
Psi semiconductor. And is this part clear? Like how we have gone about like phi n is converted to this thing. Is that part clear? EG
EC minus what is it? Phi n is what is an phi epsilon of?
n. The n
No,
type
this
semiconductor.
EC minus what is that you've written
EFN.
in between? EFN. Okay,
Yeah.
that I understood.
Yeah.
Plus, yeah, this I understood. Yeah.
Okay. Now, like this equation, we know it. And now we need EC minus EFN, right? In order to get the VB0 part. EC
Mm,
minus EFN is required. So this particular equation we have, that thing we can actually modify. So Ni, this is in case of an intrinsic semiconductor. Suppose we are taking for
mm.
an Ni, like N-type semiconductor, you can write root of Nc, Nb,
NCNV. Mm,
e power, like let KBT be here.
mm,
This minus Eg by 2 we can write as EC minus EFN.
mm.
Yeah. Is it clear?
Correct. Yeah.
Yeah. So in that case, you got this directly by substitution, right?
Yeah.
EC minus EFN. Now, if we have this value, we can substitute here and find value for V0.
Okay.
Yeah. So first, you need to start solving this thing, the equation for N. This one. First, you need to start solving this one to get
Okay.
EC minus EFN.
But NC and NV values they have only said equal, no?
Yeah,
But how do
but
you say
that
that
is when we use the
outcome?
one for intrinsic carrier concentration because everything else is given here, like what all is required. And they have given NC is equal to ND. So what happens? NC is equal to ND, EG is given. Then you can substitute all that to get the NC value.
Okay, so it becomes NC square.
Yeah. So from that you can find NC. So can you try substituting and check if you are getting NC is equal to 1.738?
Yeah.
Yeah. It's like a lot of reverse substitution.
Mm-hmm.
The questions like this, I think, are the maximum level of complications that you might face in the Excel, not more or
Yeah, but
less, because it involves like almost everything we have studied till now, right?
it involves, but how do I visualize that
Yeah.
this is what have to be done? I didn't
So,
think it.
like one thing is built-in potential for normal junction. We have a direct equation that is there in the instruction sheet. But
Correct.
whenever we are talking about a Schottky junction, that equation can't be used. So you start from the point of drawing the diagram.
Okay.
Yeah. So from the diagram, you get the first step, phi m minus
Okay.
phi n. And
Yeah.
phi n is EC minus EFN plus psi n for a normal n-type semiconductor.
Okay.
And then you again go for the Ni equation. So starting from the diagram, if you see what all is missing or what all values are not given, then you can compare with the equation sheet.
Okay.
Yeah.
Okay, I think I'll practice this. I don't know how to do just the substitution, but I see somebody else also joining. I don't know if they're
Mm,
trying to talk. I don't know.
like
There are two people.
it's the same person, they've joined from maybe two
Yeah.
devices or something. Hello, am I audible to you, Sarla Shanti? Yeah, hello.
Yes, ma'am.
Yeah,
Hello.
yeah.
Yes, ma'am. One, I'll reduce the volume, ma'am.
Like, have you joined as a student or are you from NPTL?
Ma'am?
Like, have you joined as a student for the session?
Yes, ma'am.
Okay, okay. The thing is, like, we started at 7, so we are quite into the like the session. So, are you able to get what we were discussing so far, or are you familiar with the question?
Yes, yes, ma'am. Yes,
Okay,
ma'am.
okay, fine, fine. In that case, Shanti, Sarlai, do you want to try substituting and finding whether you are getting NC is equal to this value, or do you want me to go ahead?
Ma'am, go ahead, ma'am.
Yeah, fine. And from next week, if you're planning to join, please try to join at 7 so that it won't feel like you're missing out.
Okay, okay, ma'am. I'll take that. I'll
Can
ensure.
you mute one of your phone? I think you're echoing. Yeah.
So, yeah, this is what I meant. So, you can find the value of n is given, just NC you have solved, you get EC minus EFN. So, once you
Hmm.
have got EC minus EFN, you can use it to find EC minus EFN, you get something like
Hmm.
0.19286. So built-in potential, now you can substitute. Rest everything you have already found. This entire thing is 0.19286. Psi
Hmm.
is given, phi m is also given. So you get EV0. And EV0, if you divide it, EV0, say it's some x value, then if you get V0 is equal to x by E, you just divide it by x divided by 1.6 into 10 power minus 9. So you get your V0 value.
Okay.
Yeah, that is the built-in potential in the short key. So one thing to remember here is that for normal PN junction, a direct
Only
equation is there.
direct equation can be used. Only in case of Schottky, I think to calculate that
Yeah,
EFN, we have to do that.
yeah,
Okay,
and
got it.
it is not only for short key or
EC minus
ohmic.
EFN.
Yeah, short
Yeah.
key or ohmic
Ohmic. Yeah.
anything. Depending on the figure
Hmm.
you have drawn, it might be EC
Hmm.
minus EFN, or if it's a P type, EFP minus EV might be the case.
Yeah.
Yeah. So accordingly, you'll have to change. So finally, you will get your V0 value.
Yep.
So next is width of the depletion region. Calculate the width of depletion region for a PN junction. Acceptor concentration is given, donor concentration is given, intrinsic carrier concentration is given, and temperature is given. Relative permittivity is 1.6. So
Mm-hmm.
I'll,
Give.
yeah, the equation sheet. So we
Okay.
go back to the equation sheet, and depletion width is there. If you see,
Which one is
like, 1, 2, 3, 4, 5, 6, 7, 8, 9, ninth line if you see in useful relations.
one, two, three, four, five. Yeah, W naught. Yeah.
Yeah. So that can you just note down W naught and we'll go back there.
Yeah, I can note down.
And one more thing with the equation sheet is that be very sure of what all these symbols mean. Like in the exam, what is ME star,
Hmm.
MH star. Please be very sure of those things. Otherwise, even if we have the values, you will get
I will
confused.
not know. Yeah.
Yeah.
Na plus ND into V naught divided by e raised to E into NA
Okay. 2 epsilon,
and
epsilon 0, epsilon.
epsilon naught epsilon r.
Yeah.
Okay. Yeah,
And
got it. I have
epsilon
noted.
0 is given here in useful
Hmm.
constants. That also you can note down.
Epsilon naught is 8.854 into 10
To the
raised
power
to minus
minus 14.
14.
That is the permittivity of free space.
Yeah, permittivity of free space and epsilon r is given in the question, I think. I think Na, ND, V naught is also given,
Yeah.
right? built-in potential.
Yeah, now everything is given, you can directly substitute.
The calculate the width of the depletion region of the acceptor concentration is this, that is 10 raised to 16 is Na, and donor 10 Nd is 10 raised to 18, and the intrinsic carrier concentration is 2 point. Why do we need intrinsic carrier
Need not be
concentration?
required.
Yeah. Take the temperature, also not required. Permittivity is required.
Yeah. Relative
E is
permittivity is
there.
given if you like
Yeah,
multiply
epsilon r into epsilon naught.
zero. Yeah.
Yeah, it's given. Yeah. So you have to just put the values, and
Values.
300 is
Yes.
not required, and you're not required. V naught is not given, no?
Yeah. V naught
Where
is
is V naught is not
then
given,
you'll
no?
have to find using N9. Yeah.
V naught, that's where it is. Ni square is
Required.
given.
Yeah.
Okay, got. Yeah, yeah, yeah.
So
Okay.
first you can, yeah, you can try this one. It's a direct substitution.
Yeah, it's direct substitution, but we have to find out V naught.
V
V
naught
naught is
first,
equal
yeah.
to KT divided by E. Okay.
And then Na by Ni
So
square.
in this case, you will use K in joules, right?
Yeah.
Joules per Kelvin. Yeah, and then okay.
Like no
So
conversions are required.
no conversions are required.
Yeah.
Okay, got it here.
You can just try
And
it.
then you will use that V naught in
Okay,
this,
with the
and
equation.
yeah, I think
Can you
this
just
we
try?
can get it. Yeah, I
Yeah.
can try.
And the previous question, once you get the PPT, please like go through it very thoroughly and whatever doubts you get back.
Yeah, I think I know that. The whole thought process is to get that diagram correct. I think that
Yeah.
is very tricky to get the diagram correct. So you want me to calculate the V naught first,
Yeah.
right? Or V naught? Uh, yeah, V naught should be calculated. Yeah, I'll do that. Can you give me 1.38?
Yeah.
Okay, one. I got it. Into 10 raised to minus 20. I have it. Don't worry. 1.6 into 10 into 300, right? Ln of N A is 10 raised to 16, right? 10 raised to 16
Yeah.
into 10 raised to
18.
18, correct? Yeah, 18. And Ni is 10 to 2.4 into 10 raised to 13, correct? Why did they convert Ni into per meter cube? Because they are calculating.
Like everything has, yeah, since it is a ratio, it's actually not required. I just
Not
not
required, right?
required.
Yeah,
Yeah.
you can just take
Directly use that.
2.4
Yeah.
and yeah.
But in the next, like the equation for depletion width, there is a sum instead of a ratio. There you have to convert and use. So the next equation that we will be using is for the depth of
There
depletion.
also it is ratio only, no?
No, but it is a ratio. I think it won't cancel out. I think there is something like that. Yeah,
Yeah,
we'll
it is
say that.
square, yeah,
Yeah,
yeah. So even if you take everything in per meter cube, what will happen? You will not get the, you will get the width in centimeter cube, sorry.
yeah,
Centimeter, you'll
yeah.
get the width in centimeter, right?
Centimeter, yes. Like anyway, we'll have to convert it into microns.
Okay, so you, even if you don't convert, you will get it in centimeter and then microns you have to do,
Yeah.
right? Is it okay or you have to convert it to
It
bit?
depends. Like whichever is you find it comfortable, you can try that. No issues.
Just a moment,
Yeah, yeah,
I'm
sure,
doing that. But you cannot do all these equations at once. I cannot do 10 raised to 16 into 10 raised to 18 at once, right? How do I do that?
I'll check if it's possible.
10, you cannot do. You have to. It's very bullshit. I don't know.
10 to the power 6.
If I just 16 into
10. Okay. There you have the answer.
uh,
Then you have
10, 1,
next.
and then I do multiplication, and then if I just do 10 and 18, it will not give me that.
Each time after doing the like function, you'll have to press an
Then
equal, I think. Like it goes to 10 to
yeah,
the
I
power.
did that also, but it gives a whole very big number,
Yeah, it will
and
be correct,
then
right? 10 to the power 34.
yeah, probably 10 to the power
34, yeah.
34, and then yeah,
Yeah, I think it should work. Divide.
yeah, 34 will work. Yeah, yeah, that is what you have to divide it by, divided, and then use a bracket probably. Then it'll give 23. There is a square, right? Mm.
Or like instead of multiplying, you can directly cancel those out, right? 10 to the power 34 on top, 10 to the power 20 at bottom, square L and
23.
then.
So yeah, yeah, 34 minus 23. Yeah, that is correct. Yeah, 10 raised to 11. No, it's a square there.
Yeah,
The bottom one is a square.
square, a nice square.
Yeah, so what is it is 10 raised to 24, right?
Intrinsic is 2.4 into 10 to the power 13, right? Yeah, so 2.4 into 10 to the power 13 square you will have to take. It will be 26. 2.4 square into 10 to the power 26 will be there. So that 26 and whatever is there in the numerator you can cancel out. This you need not check. This is
Okay.
in terms of meter.
Yeah.
So 2.4 square. In your case, it will be 10 to the power 26 at the bottom
Okay.
and 10 to
Mm.
the power 16 into 10 to the power 18.
18.
Yeah.
Yeah.
So these three you
So
can
16 plus 18. Yeah, this we can cancel.
34
Okay.
minus 26 and the denominator there will be this 2.4 square.
2.4. Yeah, square. And then you have to do that KT, then LAN of
Yeah.
this. 1 second. Okay, I'll do this. It requires a lot of
Process.
patience.
Yeah. And once you
Yeah,
get
too
that,
much.
yeah, you can
Yeah.
substitute here like for W0 for the width of depletion
Ah,
function.
okay. Probably they should not give us so much of substitution. They should check the technical
Yeah,
knowledge, but not the substitution. So
like the other course
probably
was
the
more of
feedback.
like that, like
Yeah,
description
that was
wise. Yeah,
okay.
this is
Descriptive,
more
yeah.
like this is
PR it
more of
is.
like
It's-
numerical, like
Yeah, okay. In a silicon PN junction, if the
the
doping
concentration
concentration in the N region is much higher than the doping concentration in P region,
region,
then
the depletion
depletion
region.
region, okay. It is inversely proportional, right? The depletion region, if in a the doping concentration in the N region is much higher than doping in P region, so the depletion region is in the P
Right
region.
on. Yeah,
Lies more in the P region. Lies almost entirely in the P
P.
side. Yeah.
And like there is a relation for finding that, like with
Yeah, Wn, yeah, this equation, yeah, Wn by inversely
yeah,
proportional to the doping concentration, yeah.
depletion region will lie almost entirely in the P region.
Yeah, something like this question should be better
Yes.
than
Yeah,
the
you can expect a
substitutions.
mix of both. Yeah.
Okay, no, I'm just kidding. Yeah, it can be anything. It's more of, yeah, what's the following is the correct order of increasing V naught built-in potential for a PN junction, PN homo junction using the following material, assuming that the dopant concentrations are the same and that all the junctions are at room temperatures.
Yeah. And for that, like, if you know the equation that relates your built-in potential with the carrier concentration, that would help. So you can check the sheet whether, yeah, V0 should be related to the carrier concentration. Intrinsic carrier concentration.
Correct.
So you see the equation and how those are related to it. Are they inversely proportional or hello?
Yeah, I can hear.
Like PN junction contact potential is there, right? 2, 3, 4, 5, 6, 7, 8 line. The one just above the depletion. V0 is equal to KBT. Yeah, yeah. So it's proportional. Yeah. So now if we go back, better. Yeah. So now if from one of the previous like sessions we had the table, right? So intrinsic carrier concentrations. Yeah, gallium arsenide is 2.4 into 10 to the power 6. Silicon is 10 to the power 10. Germanium is 2.3 into 10 to the power 13. So now they have asked correct increasing order of V0. So it should be decreasing order of Ni. Yeah. Turn and then German. Yeah. So V0 is reverse. Yeah. Yeah. So like they are forming like metal junction and there are work functions are given like the one for gold is higher than the one for lithium, and then based on whatever happens like field, like how much field and how what is the direction in which the electron move, which of these statements will be correct. This is 2.5 and this is 5. Like how does electrons move like based on the field? Yeah, like electrons move here, right? It's here. Yeah. No, that we can't. It's equal. Correct. That cannot be calculated. No, it can't be. Yeah. Since it's in the case of a metal, like once they'll have to equilibrate, right? So it might be like calculation wise, it can be 2.5 in an ideal equilibrium case, but it would not be correct to say that. Only if in a semiconductor we can say that the bend is by EV0. For a metal case, we can't. So suppose when we are forming a metal-metal junction, what happens is that at equilibrium these two lines must come what like yeah, at the same level it should come, right? So in that case we can't say that it is the difference between the two also. Yeah. So A, B and D are correct. So next is total depletion width is given, donor concentration is given. Yeah. Yeah. So in the ideal case, like if you're assuming it like to come at the center of the two, you can say that it is the difference between the two, right? No, in equilibrium case it might be, but suppose if there is an external bias or something like that, it won't be the case. That's what I meant. Yeah, it can be 5 minus 2.5 in the absence of an external field. Yeah, yeah, yeah. In that case, but then to this is wrong, right? If it is 2.5, it would have been correct. Yeah, yeah, yeah. So next is total depletion width of germanium PN junction is given, donor concentration is given, acceptor concentration is given, and we need to find depletion width on the P side alone. Yeah, we have this thing, right? Wn by Wp is equal to Na by yeah. Yeah. The thing is here they have given W. No, they have given the total one. So this is the split part and this is the total one. They have given yeah. So what you can do is like suppose if you add Wn by Wp plus 1 and Na by Nd plus 1, what happens is Wn plus Wp by Wp, right? This becomes, and this becomes Na plus Nd by Np. Yeah. So now you have this numerator, right? Yeah. So now you can find the value for W. Rest all is given. So can you try substituting? Yeah. Na and Nd is there. Yeah. Only W. Yeah. We know W. Yeah. Yeah, sure, sure. It's fine. Check. Yeah, and yeah, W0 is, yeah, and one more thing is, are you substituting everything in the same units? Yeah, 2 into 10 to the power 15 divided by 15. Yeah, 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 point 0.8, like this thing will come to point 0.8, 0.8. Yeah, you can, it's a ratio, right? Like you are telling you have taken 10 to the power 14 is common, right? 2 into 10 to the power 15 by this 2 into 10 plus 5 10 to the power 14, 10, okay? 2 into 10 by 2 into 10 plus 5. It's 20 by 25. So 20 divided by 25 is point 0.8. Yeah, you should get the same answer. Your method is correct. 20 by 25. This should be 20 by 20. Like, yeah, you had 2 in, yeah, when you cancel this 10 to the power 14 and 10 to the power 15, yeah, 20 on top, and here you have again a 2 into 10 and the 5 here. Like 2 into 10 to the power 15 by 2 into 10 to the power 15 plus 5 into 10 to the power 14. This is common. 2 into 5. So you cancel these two, you have a 10 here. 2 into 10 by 25. So that is 20 by 25. Is 0.8. Yeah, zero point 0.8 into 1.5 is W0. Yeah, that is 1.2. Yeah. So this is based on like one we have already done, directly substituting for B0. Yeah. Mm. And this too, it's a direct substitution, like finding the total depletion with A. Epsilon R is given, epsilon 0 you have to take in for the previous question. Yeah. Like sometimes how they ask is a set of values will be given like Na, Nb, Ni, Eg. Together they'll give that, and as A, B, C, they can ask in A built-in potential, B depletion, C Fermi level. So based on whatever is given in the common description, you will have to take. Yeah. So that's it. So this is all. This is the last question. Yeah. 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 And once I share the instruction sheet, yeah, you can go through that. Yeah. Okay. So thank you so much for joining. Yeah, yeah, sure. And yeah, like over meal, yeah, meal would work. Like no, that won't be permitted. Like we'll have a revision session from NPTEL's part, and the rest of the queries I'm supposed to respond by mail. So you can write to me at this mail. Yeah, there usually there will be because there are this is an 8 week course, right? So I'm supposed to take 9 sessions in total, 8 for the syllabus and 9 is the revision session. So by the revision session, you are expected to like whatever doubts you have, keep them together and then ask during that session. Yeah, that is the usual way. Yeah, yeah. Yes, yeah. Okay. Third assignment. Okay. Yeah, yeah. Mm. The drive. Yeah, sure, sure. Yeah. So yeah, thank you both for joining. Thank you. Yeah. Good. Is there anything I can help you with, Sarla? Like if you have any queries or yeah, and whatever material, yeah, whatever material yeah, I've uploaded till now. You can go through that, and if you have any doubts, you can note that down. Yeah, yeah, sure. Thank you. Yeah.